So, welcome back. Today we talk about classical general relativity, and we built the main ingredient to construct the dynamics transition amplitudes. So, classical GR, and I'll get to. I'll put some order in the various formalism that I've used, sort of mixing them up. Write the action and something about its the canonical structure, and most importantly, I'll discuss an equation, a key equation, which is K equal gamma L. I'll explain what these quantities are in a moment, which seems to play a key role at the core of GR, coming from various angles. And in addition, in my opinion, it's not entirely clarified what it means. I mean, it's clear, the equation, but all the sides of it. Let me start from the beginning. So, Einstein was of course, the first who gave a formulation of general relativity in terms of the a field, which is the Riemann metric field. For Einstein turned it around for a pseudo-Riemannian manifold, but essentially it's Riemannian geometry. He had this intuition that gravitational field had to do with geometry, and through his friends, Grossman and the other, he learned Riemannian geometry and used it. So the main point about GR is the identification of the gravitational field with Riemannian metric, but careful, because it's crucial for quantum gravity. The proper way of seeing this identification, if you want to do quantum gravity, if you want to understand quantum gravity, is not that, we have discovered that the gravitational field is the metric of space-time. It's the other way around. We have discovered that the metric of space-time is the gravitational field. Why? Because if you reduce the gravitational field to the metric of space-time, then you're confused about what the quantum version of it is. But if you go the other way around, if you just use relational space-time notions and the metric of space-time you view something extra, then you say, the metric space-time is nothing else than the gravitational field. It's a quantum field. We know how to deal with quantum fields. Just the ideology. But that's the object that Einstein used, and he got from the geometers the definition of the Levi-Civita connection, and of course the Riemann tensor. This is a nonlinear function of this one, and its first derivative. This is a quadratic function of this one, and its first derivative. And in terms of this, he wrote the theory in terms of the Einstein equations, which are the following. Okay, to which he got step by step. He got this part in 1915, this part a couple of years later. The first version, he had just this one, which he realized was physically wrong, and so on and so forth. Now, be careful that this is an integral part of the theory, the cosmological constant term. It is true that Einstein complained at some point that when he introduced it, he made a big blunder, the biggest mistake of my life, but not because of introducing this term in the equation of motion, which of course has to be there. There's no reason not to be there, because he thought that with lambda, he could get a static cosmology without realizing that it would be unstable, and in fact that the theory does predict that the universe is not static. So he had a prediction about expanding or contracting universe, and he missed it, and it had to wait for the observational people to actually measured expansion to convince everybody that the universe is not stationary. Some people realized it before, Lemaitre in particular, who repeatedly told Einstein this term is there and it does not make the universe static. The universe is going to expand. And in fact, he was the first who roughly seen the data of the nebulae, the expansion of the universe. So this term is there. The theory depends on two constants, g, which is basically measured since the times of Newton, and lambda, which has been measured a few years ago through the expansion of the universe. So this is the theory. This term here has no effect on the small, has only effect on the on large distances. As a first step, I'll neglect this term, not because it does not play a role, but because it's much easier to work without it and sort of bring it back at the end. It does play a role in quantum gravity, but for the moment, let me just forget about it. And for the moment, let's work without matter, pure gravity without it, just because it's simple. In the book is described how to couple matter to the theory I'm describing here. I'm not doing this in these lectures. The kinematic of the theory can be supplemented with matter. It's pretty straightforward. We have this spin network, and matter sits on the spin network just in the same way in which matter sits on lattice QCD. The dynamics can be extended to have matter, but let me do without it. So just this part here, just free gravity without cosmological constant for the moment. Now, immediately after, in fact, as a matter of days, Hilbert wrote this in the form of an action. So this is the Einstein-Hilbert action. He realized that this equation follow from this action here, which you know, where this is the Ricci scalar obtained by contracting this with two metrics. So contracting one indices with itself and the other with a metric. Let's for a moment work with 8 pi g equal 1, which is simple, and just put 1/2 here and use this one. Now, not long, some years later, Palatini realized that there's another way in which this can be written. This is a functional of the field g mu nu. Palatini realized that one can equally do a trick which is well known to work in finite dimensions, which is consider this field and this field as independent variables in this equation here. So let me write this as a function of g and gamma, consider two independent fields, as a square root of g. Let me write this explicitly. This is g mu nu, g rho sigma, r, actually no, g mu nu, r sigma nu as a function of gamma alone. So r is d gamma plus gamma gamma, right, with some indices antisymmetrized. So you can write the Riemann tensor just as a function of gamma, contract it, and write this action here. And it's a simple calculation to show in this action, if you vary with respect to gamma, you get exactly the definition of gamma as a function of g. And if you vary with respect to g, you get the Einstein equations. So This is an equivalent formulation of the theory where G and gamma are considered independent, and it's called Palatini, or first order. Well, this is called second order when you get the just one field. And this can also be done quite generally in Lagrangian formalism. If you have a Lagrangian as a function of Q and Q dot, you can take Q dot as an independent variable, and when you vary Q dot, you get it being the dot of Q. A key step. This formulation have a number of problems. One of the problems is that you cannot couple fermions. It's impossible to couple fermions to this formulation. So to couple fermions, you have to change variables. You have to do something. And this was realized by Weil, by Cartan, who introduced the tetrad formalism. So Cartan and Weil in different manuals. Weil is a version when usually has the formalism which is the most similar, which one is used today. Cartan has a nice, clean overall geometrical picture, which clarifies the meaning of the different quantities. The key idea for Weil is to use tetrads instead of G mu nu. So to introduce a field which is E mu I of x, where I is 0, 1, 2, 3, like mu, right? Mu, of course, is 0, 1, 2, 3. But this index is seen as an index in Minkowski space, is raised and lowered with a Minkowski metric, and the relation with this is G mu nu is the one you know well, is E mu I of x. Let me do explicit J nu of x eta ij, where eta is a Minkowski metric. Minus one. This is if you actually just take this action here, and you write G in terms of E and everything else. Here this is a function of G. You get an action, a function of E, which is square root of the determinant of G, which is actually the determinant of E, R as a function of E, and you vary and you discover that E satisfies field equations such that this satisfies the Einstein equation. It's just immediate. However, you have introduced some redundancy, because of course if you make a Lorentz transformation on these indices here, G mu nu remain the same. So there are more fields here than here, so there is a redundancy which correspond to E mu I of x going into lambda ij of x ej mu of x, which this is for every x, lambda is in SO31 Lorentz. So there is a local Lorentz invariance, and this is a local Lorentz invariant theory. You can rotate the frame the way you want. This is an interpretation, right? This is a local reference frame, and you see explicitly the local Lorentz invariance of the theory. And this is definitely more fundamental of this, because in nature there are fermions, right? So yes.
In the initial case, you're integrating over the space-time. With this integral, are you also integrating over the local Lorentz frame as well?
No, you're not integrating over. You're integrating on space-time. So let me be a little bit more d4x, and this is d4x, and this action is invariant under local. Which is pretty obvious, because this depends on E only via G, and G is manifestly invariant under it. So you're not integrating explicitly, but it's invariant under it. Right. So I insist on the fact that in spite of the way it's usually talked at school, this is not physically correct as the gravitational field because there are no fermions in nature. So I don't know how God created the universe, but definitely he did not create it with this because he would not been able to do fermions then and there would be no matter. So this is the proper description of gravitational field or something like that. Right? It's more proper this than this one. Good. Of course, you can do also the Palatini trick here, and you can consider independently, instead of G and gamma, E and its connection. Now, its connection, and this is where Cartan formula is very nice and clean, its connection is not this one, is very directly related to this one. I'm not writing the equation explicitly, they're in the books if you want. Is a Lorentz connection. Or since the connection is in the algebra, let's say in SL to C connection, because the algebra is the same, Lorentz of SL to C. So it's the variables, so first order, so let's say tetrad, first order formulation, the variables are two, is EI mu, and a connection. So a connection has a index, it's in a lower spacetime index, the one form, and indices in the SL to C algebra, which you can take to be IJ Lorentz indices antisymmetric. So minus J I mu. So these are the two independent fields, and it turns out that if you write, exactly for Palatini, if you write an action function of E and the connection, and it's just this one where you write R as a function of the connection and the E outside, you get the same theory one again. There's always 1/2, which I'm forgetting. So what it comes out to be is the determinant of E, and then E mu I E nu J F mu nu I J function of the connection, where this is a connection in a group in an algebra SL to C. This is the standard curvature, the same object you do in Yang-Mills theory. So F is d omega plus omega wedge omega. So it's a d mu omega nu omega mu nu antisymmetrized, and this is Ij, and this is I. Let's do it explicitly. Ij, Ij, I k kj, right? So you see the curvature is just a function of the connection is contracting with these things here. And this is again is exactly generativity without any blah blah blah, but with an explicit SO31 or SL2C gauge invariant, and it starts resembling Yang-Mills theory in the sense that it's very much a Lorentz connection with this extra field here. Now this can be written a little bit better in the following way. This field here with a upper spacetime index and a lower Lorentz index is not this one, is its inverse. Okay, so it's a 4x4 matrix. So let's write it in terms of this one. Well, it's easy to invert 4x4 matrix. The inversion of that is using the standard inversion formulas that you learn in Algebra 101. You get two epsilons. So this can be rewritten as 1/2. And you have to divide by the determinant, which cancel this one. So this is the same thing as epsilon IJKL epsilon mu nu rho sigma E rho sigma F mu nu I J whoops, sorry, F mu nu I j E rho E sigma E k L. So the inverse, you get the epsilon with 2. You get the epsilon this way. You have to divide by the determinant. You get this one, up to a factor of 2 factorial 2. Forget the factor of 2. Don't care. It's maybe a factor here. I don't know. And now this is nice because it allows it to be written cleanly, because if we use a form notation, which is just cosmetic, is nothing substantial here. So if we write, let's go here. If we write EI as a one form, namely E mu dx mu, okay, and omega ij as a one form, omega ij mu dx mu, and f ij as a two form, f ij mu nu dx mu dx mu, which happens to be d omega plus omega omega. Okay, it's what I wrote before, I k kj, just the convenience of the form notation. Then you see that epsilon mu nu rho sigma mu nu rho sigma is exactly the wedge product of these three things here. So the action, so now to be written nicely and cleanly, 1/2 the integral E wedge f, where the internal indices are contracted as follow. There is I, J, K, L, epsilon I, J, K, L. And let me clean up the notation a little bit also. Let me call this thing here, every time I multiply with a 4-dimensional epsilon an object with 2 internal indices, this is a standard notation, is F star KL, okay, star being the Hodge dual, just that, fancy name for that. And let me, when I have something in the algebra and something in the algebra contracted in this manner, just write it as a product in the algebra without any further so let me write this as this manner. Well, this is by definition that. Okay, so this is ij contracted with ij here. The star means there's an epsilon. So now we have a nice and beautiful action, which is just generativity again, written in a language which is particularly useful and particularly clean. Is this the action we're using for doing quantum gravity? No, there's a further step where I'm counting them, 4, 5, 6, which, since I put names here, I better go put a name here also, goes as the other names like Ashtaker, Barbera, and Holst, which did different things here. Ashtaker is the one who is the first one who realized that that's not the way he got to it. He got some another way. In fact, he found a very interesting and intriguing canonical transformation in this phase space of generativity. So he worked with canonical transformation, but canonical transformation corresponds to adding a term to the action. So later on, people understood that what Ashtaker did can be thought in terms of adding a piece to this action here. And the piece he added to this action is the following. So there's a new action, which is the following. is E wedge F star. So he added plus E wedge F without a star. And a constant here, which is traditionally called 1 over gamma. Now you say, oh, this changes the theory. No, it doesn't. Because on the solution of the equation of motion, this is actually a boundary term on the solution of the equation of motion. So if you vary this action and you vary the action without this, the classical equation of motion are the same. So gamma drops out from the classical equation of motion. Okay? Now it's pretty easy to see this because, in fact, you could guess it just by looking, because this is the same without without a star. Right? Star is the is epsilon high jk L. So star is this epsilon here. So this is a term with the opposite. Is pseudo rather. It's a four-dimensional object with an epsilon. So let's see what this thing could be if you write it in terms of Riemannian geometry. Well, it has to be something built in terms of R mu nu rho sigma. So if you vary this with respect to omega, you get the equation tying E and omega. You can transform this as a function E. You can think as a function of G mu nu, and this term here has to be this with an epsilon. And in fact, if you work out, is this term here. And you know that this is 0 by the symmetries of this thing here. In fact, there's a little theorem that the only scalar thing you can construct out of the metric second derivatives is the Ricci scalar. There's nothing else. So what about this one? Well, you just work out the definition. This is 0. So this is 0. Of course, this is not 0 identically because we used the fact that omega and E are related by what by the definition of omega in terms of E, which here comes as an equation of motion. So on the equation of when the equation of motion is satisfied, this term vanishes, which means that this thing here does not change the equation of motion. So classically, this is again generativity. Nothing is changed. There's just another action with generativity. But careful, because the action, changing the action, modifies the structure of the quantum theory without changing the classical theory. So we have a one-parameter family of possible actions here, which can give the same classical theory, which are all good for doing quantum theory. Okay? And it turns out that if you drop this term, if you put gamma equal infinity, you get in trouble with the quantum theory. Classical theory doesn't matter because nothing depends on gamma, but in the quantum theory, you cannot go to the limit gamma equal to infinity. You get confused. It doesn't work. Okay? So we need this. We need this, and we're going to use it. And that's the action on which loop quantum gravity is based. Another way of looking at this term is to think about QCD, the strong interaction. And you all know that in QCD, I should hide this. QCD is just Yang-Mills theory for SU3. So the action is 1/4 F mu nu, right? So this is the action of pure QCD for SU3 for a connection. This being a function of a connection. So this is a function of a connection, an SU3 connection, and that's on flat space. So I can raise and lower these indices with a Minkowski metric. But it's well known that you can add a term to this. The term being epsilon mu nu rho sigma. Sorry, it's not this one. Got confused. So this is this being QCD has no, that's fine. That's fine. I'm not confused. Mu nu rho sigma, F mu nu, F rho sigma. So there's an epsilon term you can add, and with a constant here, which is called theta QCD, which is believed to play a role in QCD. I'm not going to that, but there's all this literature about the role of this theta QCD in QCD. So it's exactly the same thing. It's this does not affect the classical equation of motion, but it has an effect in the quantum theory and is believed to play a role in some particle physics phenomenology, explicit. So it's just to say that it's not something very peculiar to gravity. It's something which is the existence of these terms is common to gauge theories. So good. So this is the action we're going to use, and let me write a little bit better. Obviously, the
this is the only additional part that you can add, or are some others? I mean, why? I mean, how do we see that it's the only one? If it is the only.
Depend on the freedom you give yourself.
Okay.
Alejandro Perez has studied all possible terms you can add if you want to work with an action which is polynomial, is geometrical in the sense in which you can write it as wedge product of E and omega, and he has a finite number of a small number of possible terms, which are not just these ones, but this order of 4 or 5. So there are other possible terms. One possible term one can add is the cosmological constant, right? This is so, which here in this language is just E wedge E, wedge E, wedge E, lambda with the indices suitably contracted here. I'm not epsilon, I suppose. Yeah, epsilon ijkl, epsilon ijkl is the determinant of E. Yes. So in this notation here would be this wedge, this star. This is the action used for doing loop quantum gravity. It gives classical generativity in the limit, and this is the quantum theory on which it is based. So I'm not claiming this is the most general term. What is interesting is that the number, and that's what Alejandro was puzzled about, that the number of possible terms you can add if you want polynomial and geometric is finite. Which means that one is tempted to say that normalization theory cannot produce an infinite number of terms because there aren't an infinite number of terms. It's a bit delicate because, of course, perturbation theory around what? If you go around E equals 0, you don't have the standard perturbation theory. If you go around Minkowski, then you break Minkowski by itself breaks the invariance under which these terms are finite. Good.
So,
yeah.
In principle, one could start from higher derivative theories of gravity.
Yeah.
Okay. So, but in that sense, in that case, they will be infinite, right? Infinite but finite number of derivatives. So
The field theory, which is higher derivative theories, is a different field theory.
yeah. Okay.
It's not GR.
Okay. Okay. So you will start from GR.
I'm not saying that we are studying the most general theory for a metric. We are studying GR.
Okay.
Okay. There are many alternatives to GR. The space of possible theory is infinite, and of course, some of them are ruled out by experiments. Brandstick is a great alternative to GR. It is basically ruled out by solar system measurement. A lot of alternatives to GR have been largely ruled out by the recent observation of the merging of the neutron stars. So there's nothing true by unicity. There are theories which are supported by experiments which are studying.
So, but if, for example, Planck or some experiment shows that, I don't know, traces of inflation tells you that there are r squared terms, for example, like not just r, but r squared, in principle one could start from the same formulation and do what we used to do now in quantum gravity.
Yes, yes. So yes, absolutely. So if we have evidence, and one may even claim that inflation is an evidence for an r squared term, because if you do the Starobinsky way, you could interpret the inflaton as the extra degrees of freedom that comes in the theory whose action is r plus r squared. Then you have the same kinematics but the different dynamics. So you could use the same kinematic of loop quantum gravity and change the dynamics accordingly. So yes, definitely. Good. So let me write this in a slightly different form. So again, the fields are E and omega, and here I can shift, if I want the star on the E, right, it's just an epsilon. I can say that the epsilon act on this indices or on this index is the same thing. So I can rewrite the first terms of E wedge E star wedge F, and the second terms is just 1 over gamma E wedge E, so I can write here plus 1 over gamma E wedge E, and put this in parentheses, wedge F. So this is the action of GR. Again, this is just standard general relativity in slightly different variables and with an action which still gives the Einstein equations in the classical theory. And this can also be written, interesting, as B wedge F, where B is a two form, right? With indices in, so it's B mu nu ij if you want. So with antisymmetric SL2C indices, so this is the algebra of Lorentz, it's a two form in the algebra with values in the Lorentz algebra. F is a curvature for a Lorentz connection, for an SL2C connection, where, however, B is not generic because not every B fields can be written this way. So where B is constrained to have the form B E wedge E star plus 1 over gamma E wedge E. Okay, so this is again GR. Is the theory of this action where B has this constrained form. Now, why this is interesting? Because these theories are if we didn't have this relation here, we would have a different theory, of course. Okay, it would not be GR, and this theory called BF. So this alone is called BF action. And a lot is known about these theories, and in fact, there is a very clean quantization of these theories. Obtained by discretizing space-time, discretizing this thing here, both the two fields, and writing the transition amplitude, or if you want the partition function, in a very natural way. These were studied for a while by people. I will say something about that. We'll describe that. So. Generativity can be seen as one of these theories which we know cleanly how to treat, plus a condition, which is this condition here. And from this condition, some interesting relation on B comes out.
I'm sorry, I didn't understand. The BF theory, it's a theory.
It's a theory for two fields, B and a connection.
Okay.
okay, which has simple equation, because if you vary B, you get F equals 0. And if you vary the connection, you get dB equals 0. So the equation of motion are very simple. F equals 0. And the covariant derivative B equals 0. So it's a flat connection and a covariantly constant B. So it's a very simple theory. But it's a theory whose quantum theory has been studied in detail. And I'll get to that. And general relativity, it's not that theory, okay? It's related to that theory by having the same action where, however, B is constrained to have this form. And since B is constrained to have this form, you cannot vary B freely, so you don't get this equation here. You get a weaker variation, which instead of that gives the Einstein equations, which are weaker than curvature equals 0. Is Ricci equals 0, not Riemann equals 0. But it turned out that it's sufficient to constrain B to have this form for weaken this and to get exactly Ricci equals 0. Now let's look at this relation here a little bit more in detail. And remember that we want to study the theory on a compact region, space-time region. So in space-time, we want a compact region, four-dimensional region, R, bounded by a three-dimensional surface, space-like, that's called sigma, which has a past part and an upper part. And we're interested in the transition amplitude for this to this, or in the classical theory, the Hamilton function, which depends on the coordinate here and the coordinate there. Now, in the Einstein formulation, the field is g mu nu of x and t. And when I am on this surface, I can always choose coordinates such that locally this surface is given by t equals 0, and choose coordinate x, which label the surface here. So I can always locally have this with a parameter t equal a constant, some initial t, and this also, or 0 or some constant, and the three coordinates x labeling this one. And locally, I can always put this, choose a gauge where this has the form 1, 0, 0, and a 3 metric here, GAB of x. Where this is a 3 metric, which is the induced 3 metric from 4-dimensional to this surface here. Okay? So given a metric in space-time, it induces a metric here. If I choose in space-time this coordinate, is just what sits in the 1, 2, 3 component of the metric, very simply. And this can always be done. Look, this is called the time gauge. It's the first meaning of time gauge. Time gauge means a lot of things, but this is the first meaning of time gauge. And this three-dimensional metric, which actually called QAB in previous lectures, sits here and sits here. And if I call this the initial and the final, the Hamilton function depends on this and that. And the rest is gauge fixed, so I don't care about the rest. Right? Now, of course, if I use tetrads, I just have tetrads here and tetrads here. But there's something more that I can do. Because if I have tetrads, oops, it's 10:45. Time flies. So if I have tetrads, come back in 15 minutes and you'll know what happened if I have tetrads.